Research affiliate at Lawrence Berkeley National Lab. So today my topic is direct entanglement ansatz learning with zero noise extrapolation on superconducting qubits. I know this workshop is about artificial intelligence, but I want you to think about these methods using your computer science mind. This work is actually inspired by the Edward Farley. He's the inventor of quantum approximate optimization problems. He invented this problem back in 2014. And then I'm lucky to be in the University of Maryland for his talk. It's really inspiring. I do recommend you to see that. So I also want to quote Richard Feynman, said in 1981, by golly, it's a wonderful problem because it doesn't look so easy. Before I get started, this research used the resource of Department of Energy, contract with IBM Quantum Computing Center. So this is how we get access for the IBM quantum hardware. And also this research is supported by high performance computing centers by Texas Tech University. And then if you scan this QR code, you can look through our paper. And then here's our team. So the motivation for this work is actually inspired for the quantum hackathon back in the Calgary in Canada. It was happened last year, and then our team called Fantastic Five. I know it sounds a little bit stupid, but we won the first prize to solve the combinatorial optimization for snowplow problems. So what is combinatorial optimization problems? So imagine we have n bits, you have zeros and one, and m clauses. So for quantum system, you have spin up and spin down. Basically just, you have 0 qubit and 1 qubit. And then you want to use your quantum system to match the classical problem exactly. So here we want to maximize the capacity of the quantum model to match the classical problems. So in other sense, we want to make this ratio big. This is a success ratio. And then if we look back into 2000, the initial idea to solve the combinatorial using classic algorithms is basically based on the random guess, and then it's 50-50%, and then plus the constant error rate. And then back in 2014, Edward Farley proposed quantum approximate optimization problems. And then he utilized the quantum Hilbert space to improve the classical algorithms using the different variable improved by 4/3. And then after 1 year later, some top computer science team introduced a better result classic algorithms by further improve these algorithms by doubling it up. And then you can see the computer science group right here. I do recommend you see the Scott Arison's blog. It's really interesting. So how do we prove the quantum advantage? If we look at the QAI warm start, we have mixed Hamiltonian and cost Hamiltonian. So cost Hamiltonian, basically you need to map the classical problems into the quantum Hilbert space. So this is exact translation. And then for the mixed Hamiltonian, you can imagine this is a driver function to push the quantum system to find the lowest energy. And then if you look at the right plot, it was proposed by Parisi back in 1979. So he proved the optimum quantum system value is about 76%. So how do the Edward Farley prove the quantum advantage? It turned out to be 3 years ago. They used a random graph optimization problem to verify the algorithms using a deeper layer of the QAI. And then they used tensor network simulation techniques, and then it's exactly matched to the optimization of the classical algorithms. And then we found there are some tricky problems if you use different graph. So their graph is used the complete graph as shown in the middle here. You can see if you want to partition the graph, you have J and K, and then all the edges are connected, and it has no coefficient. And also it could be represented by the tree tensors. But if you have some graphs like Andor running graph, because the edge probably disconnected based on certain percentage, and also this has some coefficient, these might be some tricky problems. And if the worms start good, it totally depends. So we propose direct entanglement and source learning. And then on the left side, you can see how we leverage. If you see the performance gap we pointed right here, use the purple method, use a purple color. We run these algorithms by couple, like hundreds and thousands times to prove the Monte Carlo simulation, verify the algorithm performance is actually better than the original QAI. How do we verify it? We utilize the KL divergence and then compare the quantum methods with the classic definitive optimized value. And we want to minimize the layer. We want to minimize the distance, use the minimized QAI layer. For example, the original work proved it from one layer increased to 11 layers. And then we want to use the minimum layer to achieve the optimized values using our methods. And then you can see the difference right here. And then on the right side is actually our proposed algorithm. I will walk you through bit by bit. So the core component here I want to emphasize is qubit prioritization normalization techniques. What is that? So Dr. Steve Hyatt proposed, why don't we directly use the coefficients of the original problems and then to encode the coefficients directly into the quantum state amplitude. So if you have 4 qubits, how many states do you have? 16. And then you have different quantum gates encoded into parameter quantum circuit. And then we want to directly input the coefficients of the problems into the quantum gate parameters. And then how do we encode it? I want to redirect you to the expectation encoding techniques. So we basically just introduced an extra layer, used arc cosine and arc sine function. Because if you look at the bottom graph, the bottom plots here, if you verify it using x and y basis, the qubits is very interesting because when you rotate the qubit, it has cosine and sine function. And then if you add one extra layer of arc cosine, it turns out to be negate with each other. So if you look at the solid lines here, you can see the observable discrepancies between two bases. So for the cos Hamiltonian, we use arc cosine. And then for the mixed Hamiltonian, there's no similarity between, there's no difference between using the arc cosine and arc sine because x, y both have the gap discrepancy between the two observables. And the next steps is how we encode the quantum answers into the physical quantum computer. And then we know we're at the next era. The quantum computer is quite noisy. So if you look deep into the IBM quantum hardware, they use fermion-based superconducting circuits, and then they introduced the Joseph junction. So it actually is totally based on the pulse values introduced into the QPU. And then how we solve this problem without introduce ancilla qubits, like extra qubits. So the first technique is coordinate with our mixed Hamiltonian is over rotation. So imagine you have theta value. That is the first value you want to encode. And then lambda is the extra coefficient you want to introduce. And then if you over-rotate the qubit, you actually rotate it more and then introduce more noise. And then to fix this noise, you increasing the lambda value, and then from 1 to 1,000, and then you can approximate the error rate ratio. And then you can use the Gaussian model to extrapolate the errors to remove it. And then another technique is to introduce the gate folding techniques, because in QAI layer, you have some qubits idling. when you do the qubit rotation. So by introducing the qubit gate, by sandwich the original qubit rotation you want to encode it. So you introduce more coherence times using the IBM quantum hardware. So this is how we solve the noisy issue using in our methods. And then if you look at the result, we tested it based on the 3 typical combinatorial problems. One is the left side is travel salesman, the middle side is knapsack, and the right side is max cut problems. We want to emphasize the left side. You basically can see there are 2 optimized values here because travel salesman problems have 2 directions. And then if you verify it to find the lowest Hamiltonian, you can find the 2 optimized value. And then how does it look in the real quantum backend? You know, IBM quantum hardware, they will encode the quantum ansatz you proposed and then into the physical layer into their quantum processing unit. And then they use the entanglement they use the entanglement gate called control Z gate. And then these control Z gates will increase based on your QAOA layers. And then this increase linearly based on your QAOA specification. So here you can see our methods improve based on the original QAOA benchmark. And then we really want to test the minimum QAOA layer if you look at the x-axis. So if you look at the around 8 layer, you can see that there is some decay value after we increase the QAOA layer. This is because the quantum processing units will introduce some crosstalk error, and then these are unavoidable for the noisy quantum backend. And when we use the quantum hardware, is what's called Marrakesh. I think they recently released 2 state-of-art quantum QPUs called Kingston and also Pittsburgh. It might perform a little bit good, a little bit better than this one, but because we really want to stress out the quantum processing units for our algorithms. So this is why we want to test out the QAOA layers. And to conclude our algorithm, we introduce a qubit prioritization normalization technique. And then worst case performance guaranteed by the minimum layer using 1 to 3 layers. And then performance improved with the depth, but hindered by the noisy quantum hardware. Theoretically proved with phase difference by using the extra layer of arc cosine function. And then it appears the plausible results on near-term noisy quantum computer. It is possible that we can obtain the quantum advantage using the fault tolerance quantum computer in the future. And then on the right side is our envision about the future quantum hardware. If IBM can did what they said in 2029, so we can probably achieve the quantum advantage in the QAOA-based algorithms. With that, thank you very much.
Wonderful. Is this mic working? Thank you very much for a really great talk. This paper is now open for questions. We have microphones to help folks that are calling in online to hear your questions. So does anyone have any questions for the speaker?
Yeah. I didn't understand the argument about the rotation when you just increase the angle and then you boost the noise by increasing the angle. Is that correct?
Yes.
And you are putting the RZ as an example for a superconducting hardware, right? But as far as I remember, RZs are frame shift operations. How they are bringing noise into the system?
Yeah, so the mixed Hamiltonian we use is RZ rotation. And then RZ rotation is around Z-axis. If you rotate it, it basically introduces phase errors. And then if you, for example, if you rotate it 45 degrees, it is, if you use the tangent edge to encode the theta, that will be 1. And then if you over-rotate it for 90 degrees, that was 0. So by over-rotate, it basically changed the phase error you experienced. And then if you use the Gaussian model to approximate this error, you can find the pattern of these errors, like 1, 0, 1.5, and then 3/2. So it has some certain pattern if you do this iteratively.
Does anyone has another question?
So what is the largest number of cities your algorithm could help for the traveling salesman problem? How many cities, how many cities could you handle?
Currently we test 5 nodes. Sorry, I think I have a backup slide. Yeah. The nodes you want to handle is really depends on the physical hardware. So the reason we do not test the nodes like to 150 nodes using IBM quantum hardware, because we want to increase the layers of QAI. And then currently the main bottlenecks for the QAI algorithms is the layer, because if you read the original paper proposed by Edward Farley, they want to emphasize this algorithm to approximate the best optimized value using the deep layer. And then the nodes just depend on the hardware you want to use. Yeah.
I mean, to achieve quantum advantage, seems like they're pretty far away to go, right? In terms of the traveling salesman problem. Because the classical algorithms can solve like up to millions of cities. I don't know what's the state of the art. Could you comment on that?
The state of art will take exponentially times based on how many nodes you want to use. I think currently it's like not millions nodes, probably 100 nodes. Yeah.
We have time for any additional questions from the audience. And if there's anybody on the Zoom call that would like to ask a question, we have plenty of time. Well, if there are no more questions, let's thank the speaker for a wonderful presentation.
Thank you.
So we do have a bit of time before our next scheduled talk. Our next scheduled talk will begin at 10:30. In the meantime, I would like to also ask if the third speaker for today is in the audience and you would like to come up and upload your slides, please do so. Or if you're online.
Hi, I'm online.
Okay, great. So we are well on track for the remaining 2 talks of this session. The next talk will start at 10:30. Okay. I think this was you, right?
Yeah. The screen is shared.
The screen is being shared continuously on the Zoom.
Okay.
GPT powered QA. Yes, there's a transformer outside. Yes, transformer outside. So we use algorithm-based technique for it. And then to one the initial
So when you use GPT for initial, there was a typo. It's warm start, not warm smart. That's okay.
we knew what it meant.
We get it. Yeah. Maybe we call it smart. Well, yes.
Sorry.
Yeah.
Smart sounds more like AI.
Yeah, exactly. I thought it was probably fun. But anyways, so what, then you need to train it first with some sort of data set. Where would you?
They use pre-train.
Right, I know. So where's that pre-trained? It's transfer learning from something else. Or where they transfer that learning from? What model?
Fine-tune something. Yeah, I didn't read the paper detailing, but their idea is using synthetic data, proposing the QAI classic framework. And then they use that data to fine-tune the model to find the best initial answers for QAI second.
Yeah, because I mean, because when you talk about quantum AI, quantum for AI, AI for quantum. So now they're saying, why don't we just use AI to help with quantum? So they bring a lot of AI stuff to one start, the quantum algorithms.
Yes.
Yeah, and then maybe you can deploy another AI error correction routine to if you hope to possible. So basically AI in quantum and then AI again. So QAI becomes an AI quantum iteration instead of just like, because essentially what you're doing when you're trying to optimize your classical route, that's where AI is best. So you can probably just create that.
Create a circle.
Yeah, whether it's called GPU or something.
But the creation of the answers happens just once. They are in the learning tools, right? In the learning
Yeah. So the only part that's quantum is
Just the QAI.
Yeah.
but the optimization part is still classic.
yeah, but you can probably, I'm just thinking, since you're going to use AI anyway, why don't you coordinate with the, because it's like warm start. Warm start is basically you are reducing the iteration.
Yes.
Using, like condensing, using, it's like somewhere else you've done that iteration, and then you drop it in.
But the only thing is related to the agents, the AI skills.
Yeah, well, I mean, sure.
What the AI will be simple, it's very simple, but we give you a very update.
Yeah.
That would
Because so you basically do error correction or some other routines. So basically you use that to take care of a lot of stuff before you log it back. So it's like warm start, but every time you do warm start.
Every time we do one step.
Yeah, so basically you're getting much, so I think there's another thing that did, even in the optimization, I think it's probably some concept is that they're actually introducing almost like a runtime update. So they don't just use a fixed optimization. The idea is the same, is that you're optimizing the optimizer using AI. As you
changing the equated parameter.
yeah, exactly. Yeah. So basically, you
Based something on the performance.
that's the current version of quantum AI. Quantum AI.
I've been thinking about that because there's another way.
Sure.
We don't know if the AI will give you very good answers, so we will compensate for latency.
Yeah.
Or yes,
I mean, sure. Yeah. I mean, so maybe you sacrifice the latency,
but
get
we
better.
get better results.
Much better.
And probably the convergence
But then-
will be sooner.
Yeah, but then because of better result, you reduce the number of iterations.
Yeah.
So it's, yeah, so it's word trying that.
That's a great suggestion.
Where's the mouse?
Another actual layer.
Is there a mouse here? Or
Are you looking for,
just, like just in case I need to point somewhere on
oh,
this?
let's, yes, there is,
What is-
should be, down here. That little thing that looks like a paintbrush, click on it. There's a laser pointer.
Okay, okay, I see.
And then the arrow keys will help with the slide advance and
Okay, so can I still hide this? Or no?
I think so. Let's see if it keeps the,
Okay,
great.
okay, thank you.
Alrighty. This is just a 2-minute warning. We're going to get started with the technical material in just about 2 minutes, right at 10:30. All right, it's about 10:29, so I'm going to introduce the next talk, which is, I can't even say it, Statistical Time Series Modeling of Quantum Systems Using Rough Transformers. And again, you're welcome to join the Zoom meeting in the room. If you do, please make sure that your audio is muted.
Okay. Okay, thank you all. Good morning, everyone. Thank you for being here. So I'm Xiwen Liu from Florida State University, and today I'm going to present our work on statistical time series modeling of quantum systems using rough transformers. By quantum systems, I mean a quantum circuit that is implement a particular algorithm on a real quantum computer. Okay, this is the joint work with Johan Shao, Chai-Shi Islam, Sam Jacob, Ryan Carmack, Jake Scaly, and Bayan Oregon. And we are from FSU and FSU College of FAMU FSU College of Engineering. And I will start with a different project, but that motivates the current project we have. And many of you may have recognized already, and this is a particular implementation of the Bernstein-Modigliani algorithm, and for a particular string. And many of you may have know, and for this, if you want to solve this algorithm classically, and you need to have n queries, n being the number of bits you have in the secret string, right? And we all, at least I know most of you know, right? It's a classic. If you use a quantum algorithm by using superposition and the interference, you can solve this problem using only one query. At least that's the theory. Okay. Now, when you run this on a real quantum computer, however, it's very different, right? For example, this is the result we have. We also run our algorithm on the IBM machines, and we use the 10 minutes free times every month you can get. So this is on one of the machines. I think it's a quantum. I think the details doesn't really matter. And you can see from here, if we run on the quantum hardware, rather than getting a one correct solution all the time, right? And you can show here, here's actually the correct solution, but actually it turned out to be very noisy, right? We run, this is over 10,000 shots, and the correct solution, the probability of the correct solution is actually pretty low, okay? So basically, given this, right, the question is, right, how can we improve, right? How can improve the, how can improve the success rate on real quantum computer? And one of the ways we have been doing is to use quantum error mitigation. So we have developed a number of techniques. So one of the techniques we developed is to think the noise essentially as a filtering process that essentially gonna essentially blur the outcomes, okay? And since this is a filtering process, or in EE, this is a convolution, you can essentially do deconvolution, and we implement Richard-Lucy deconvolution algorithm, and this is one of the examples you can see here. Essentially, the red bar is the correct solution, and the height of the bar showing the probability, right? We can see by running the algorithm multiple times, and we're able to get the correct solution to be with the highest probability. Okay, so, and we test our algorithm on 2 different data sets, but I don't want to go through the details. In general, we are able to improve on average the rankings of the correct strings, right? So on average, even though in some of the cases, and we do not improve, but on average, we are able to improve. On this data set, we improve about 1 position, and in another data set, we were able to improve more. And compared to if you compare the state of the art, right, we compare 2 of the state of the art, one is called the hammer, the other one called the QBIP, and in general, both of the algorithms, neither of them was able to improve on this data set. Okay. So this is what we did. And however, the problem we run into is in order to run the Richard-Lucy deconvolution, we have to set some parameters, right? And those parameters, it's going to depend on the characteristics of the circuit. And however, those characteristics depend on, the machine you have, depend on other things, okay? So basically the question we want to ask ourselves, is there any way we can maybe learn, right, the dynamics of the system and use what we learn and to help us choose the parameters automatically. Okay? So we used a particular IBM quantum computer, and obviously we don't really know all the details, right? If you know all the details, you might be able to derive based on some kind of first principle, but at least we cannot do that. So basically, what we ask ourselves is, can we learn an approximation of the dynamic function of the circuit that would be useful for applications, okay? So that essentially motivates this work, right? So this is the outline of my talk, the rest of the talk. Right, so we all know quantum systems are highly stochastic and very noisy, and for at least the application we are interested in, the outputs are sequences. Right, since they are sequences, we can treat them as time series. Right, for the time series, time series modeling is a common problem used in many different areas, but they are now, right, there are also many models developed for health, finance, and the weather, but those in general, those traditional models do not work well for the quantum stochastic in order to model the dynamics of the quantum computer systems. Right, the goal here, we want to build a model that can capture the distributional behavior of quantum computers. Okay. So, right, as I mentioned earlier, you might be able to, simplify with based on some of the assumptions. You might be able to get a model that can simplify the process. But in general, if the assumptions do not match the computer, then the accuracy is going to be low, right? So even though there are many works on modeling time series in classical application, there are not that many for modeling output from quantum computers, right? There's one recent work by Wang and Wang, and essentially they use a transformer to model the dynamics. However, dynamics is limited to 1 qubit, right, of an open system. Right? If you're interested, the reference is at the bottom, right? So basically, what we like to do is want to capture the complex interactions among multiple qubits in a real computer system. I think this, as far as we know, this has not been explored, right? So to do this, we're going to propose to use rough transformers and with a Hamming distance-based label smoothing. And these are the two components, right? We're going to use the rough transformers and also the Hamming distance label smoothing. And again, we're going to focus on statistical fidelity using Kuba-Libler divergence, right? As we know, because the series are inherently stochastic. There's no way you can predict exactly the output at a particular point, right? However, right, our goal is to be able to match the statistics from a real quantum computer. So I'm going to first talk about the first component is the Hamming distance label smoothing. I don't know how many of you are familiar with machine learning techniques, right? So when you train deep learning models, right, many of the deep learning models are trained using cross entropy loss. And that loss, however, oftentimes going to result in a model that's going to overconfident, right? The reason being that you can really minimize the loss as much as you can, as close as possible to zero. That's going to really drive basically the probability to be as close as to 1, whether it's correct or incorrect, okay? So one of the ways to overcome that is to use label smoothing. The basic idea of label smoothing is rather than label the outcome as a one-hot encoding, essentially you encode it as a mixture of one-hot encoding and plus the uniform distribution. Okay, so, but in our particular case, we know for the sequence we have, it's not uniform, right? There's a structure. If you look at the sequences, in the Hamming distance space, that means if you look at the distance from the Hamming distance of each outcome from the correct string, right? Obviously, we cannot do that during the test time, but we can do that in the training time, right? So essentially, this idea, we're going to use this Hamming distance-based label smoothing as a regularization term. Okay, so here the regularization we have, right? This 1 minus alpha here is a smoothing coefficient, and we have default value of 0.1. That's the value we have used in our experiments. And this essentially 1 minus alpha and this is the one hot encoding term, and we distributed the rest, it's the alpha to the other classes, and this essentially depends on the Hamming distance and also how many of them in that group, right? I think we call the Hamming distance bin. Right, the other key component is the rough transformers. I know transformers are very popular, right? And they are the underlying architecture in ChatGPT and other language models. And in this particular one we have, this is a particular transformer. It's trying to capture the sequences, especially the stochastic nature of the output from quantum computers. I think the best way to think about this is the price on the stock market, right? Because it's hard to predict the trends correctly as well. So one of the well-studied ways to do this using what's called path signatures. So roughly speaking, this essentially allows you to compute the signatures, okay, that characterize essentially different kind of patterns in the data you have or in the sequence you have, okay? So that's signatures, and for the rough signatures, and there are two kinds of signatures we use, okay? One is the global signature is trying to capture the data in the entire context window, okay? That's the global signature. And plus, there are also a number of local signatures trying to capture the short-term fluctuation. Okay, so essentially together, this will allow us to capture the multi-scale variances and patterns in the data we have. Okay, and then after the signatures, and then that's going to be followed by a more or less standard transformer. Okay. However, these transformers are not based on tokens, but rather is based on the embedding of the path signatures. Right. So here is the architecture, and right. This is essentially mainly the multi-view signature transformation. And this part is mainly going to be the transformer. I'm going to show a little bit more detail in the next two slides, right? So we have given the input, since the input is going to be sequences, and we do a piecewise linear interpolation, this become continuous, and also by doing this, and we don't have to assume the sample to have regular interval. Essentially, that's going to have, right? You can think this model inherently can handle essentially continuous sequence, the sequence with continuous value. Okay? And this essentially for us to use the loss, right? This is not going to be, this is only there in the training set, okay? And for the multi-view signature, we have the global signature trying to capture what's going on in the entire sequence that is available, and then local signature is essentially going to divide this into multiple windows and then capture the signature in each of the windows, right? And given the window and given a context size, and we're going to using a local slide window to cover to capture the local signatures within the window. And this essentially together we concatenate and truncate, and this give multi-view signature. And this multi-view signature essentially going to pass this one through a signature embedding layer. I think this is, I don't know how many of you are familiar with transformers. Essentially, that's corresponding to the embedding layer in a typical transformer. Okay, so, and with the transformers and with the embeddings, then basically these are the standard transformer, more or less standard transformer layers. And you may have heard, right, a key feature of transformer is essentially multi-head self-attention, right? We have the multi-head self-attention, and we also have the feed-forward network layer plus layer normalization, and these are the standard. These are standards in any transformer implementation. Okay, and typically you're going to have multiple layers of this, right? For the problem we have, we use 4 layers, 5 layers, 6, and 7 layers. Or you can, in general, you can use any number of layers, but for the problem, for this particular study, we use 4, 5, and 6, 7, maybe a few more. But in comparison, the transformers for underlying ChatGPT, they use a lot more. Okay. Right, and then we also going to evaluate. Right, when you train a model, obviously we have to use the loss that depends on the smooth labels, and we also estimate how well we can capture the sequences, and this is based on KL divergence. And however, this KL divergence is not between the label accuracy, it's between the sequences predicted by the model and the accurate sequence from the computer. Yeah, so we have generated a small data set that's using a IBM quantum computer, and the one we generate is based on the Bernstein-Wadiani algorithm, right? Those are the circuits we use. And I had an example earlier. Basically, the circuits, the detail of the circuit, and the gate use going to depend on the string, the secret strings you have. To vary the secret strings, essentially going to have a different circuit. And we also have to deal with one detail, right? If you, I don't want to jump back, so I may not be able to come back here. So anyway, though some of the classes going to be very rare. So in that sense, you may not have enough samples in those classes. So we group those together so that we can have enough samples. Okay, so this is what we call the label compression. We group them into a different number of classes. In general, we're going to have 5, 6, 7, and so on. And then the model we have, right? We have this rough transformer, and with the regulator, and that's going to be trained on A100 GPUs, and we use PyTorch, and the optimizer we use Atom. Right? These are the standard algorithms that people use. And this is the main results we have. Right? We have here we're showing 2 sequences, and the first 2 are the same sequence, and the Hamming distance, the group, the first one using 5 groups, the other one using 7 groups, and for each of them, we also vary how many layers, right? This is 2 layers, 3 layers, and 4 layers, and this is the learning rate we have, and then we have the training accuracy, and for the training accuracy, in general, because the sequences are very stochastic, we do not expect the accuracy to be very high. But if you choose a small learning rate, and you can increase, basically you can increase the training accuracy to be high, that means the model can fit the actual sequence you observe. But this is very different from traditional sequence modeling. You can see here the validation accuracy is low. Okay, it's because we do not. This is expected because we do not expect we can predict precisely what the next point is going to be. right, due to the nature of the quantum computers, right? And similarly, the accuracy on the test is going to be low as well. That is expected as well. However, right, if you look at the QAI divergence, this is the QAI divergence on the test sequence, and between the test sequence and also the predicted sequence we have, right? And you can see here, the QAI divergence is small in all the cases, is showing that the rough transformer we have will be able to capture the statistics in the sequence generated by a real quantum computer. Right, and we observe this for other sequences. We observe in general similar behaviors. Right, we also trying to plot how much variation we have, right? And we can see here, when the number of sequences is short and the QAI divergence is going to be large, that's expected. And as the sequences become longer and the accuracy between the predicted one and also the actual one become much smaller, right, according to the QAI divergence, and also this is very stable, right? And so this one, the channel area showing the one standard deviation of the difference. Right, we also, on the same data set, we also compare with the multi-layer signature regression model. Right, here is the output from a regression signature model. Right, even though it's using signatures, our regression can only capture essentially the mean behavior, roughly the mean behavior of the sequence. It really cannot capture, right? If you look at the red line, essentially showing the observed data. Okay, this is very noisy. Right, so in comparison, the model we have was able to capture the differences much more accurately, right? And you can also see the loss function here and remain to be high. Right, so in this work, we have introduced, we call the R reformer, essentially a rough transformer-based architecture with regularization. And we have proposed this new Hamming distance-based label smoothing at the regularization. And we propose a QAI divergence as the objective function. We believe this is the first model which is able to model the output sequence from real quantum computers accurately. And this also enables new applications, including calibration, error modeling, and generative AI. You can basically generate the sequences using the model we have learned. And I would like to acknowledge a grant from NSF, and also like to thank the organizer for the workshop. And thank you.
Wonderful talk. Thank you very much. The paper is now open for discussion. Are there any questions for the author?
So when generating your data set, do you do a certain number of runs to gather all this data of the circuit across the IBM computer? In other words, is it 10, 100, 1,000, or do you just are doing one run to generate that data set?
We generate one run, but we generate for each of the cases, we generate one run, but that run has, typically we have 10,240 shots.
Okay, oh,
Yeah.
shots is
Basically, yeah, it's a sequence. It's not multiple runs, but it's a sequence from.
Okay,
Yeah.
got it. And then the second question was related to the labeling. You said that you group some that occur at low probability. Is there any thoughts of just casting some of those out?
Yeah, so basically, right, if you group them into bins, you can see Some of them do not really happen very often, and basically, in machine learning terms, you're going to have very unbalanced classes, right? So basically, we group them, trying to make the data a little bit more balanced.
Thank you.
Thank you.
Are there any other questions from the audience in the room? If I could ask a question?
Sure.
You mentioned that this method would be good for noise characterization. Do you have an idea of how sensitive it would be to identifying whether the noise of the hardware has drifted or if the noise has changed significantly?
Oh, you mean if the noise change over time?
Yes.
That's a good question. So basically, currently the transformer is going to learn how to generate sequence, but that sequence is not going to be, the model itself is not going to be time dependent, right? Even though it can generate the sequences, I think if during for the entire sequence, if the beginning is less noisy, then the end becomes a lot more noisier. I think we have to basically introduce time-dependent parameters to be able to handle that. The current model will not be able to handle that.
Thank you. Are there any questions from the folks joining us online? Okay. If not, let's thank the presenter again.
Okay, thank you.
And the third speaker, I know you are online.
Yes.
So I'm going to try and stop presenting so you can share your screen.
Sure. Please. Thank you. Can you see my screen?
Yep, we can see your slide deck. It's like in, I think we're seeing one of the last slides of the deck, or, sorry, the fourth one.
All right. Can you see my screen now? In full screen mode.
All right, that looks great. So for the third talk of this session, we'll be hearing a presentation on adiabatic quantum linear optimal control for discrete time dynamical systems.
All right. Hi, everyone. Good morning. So thanks for organizing this excellent workshop and dedicated to this theme of quantum AI. My name is Ben Cha. I am associate professor in University of Lorraine in Nancy, France. And this work has been done in collaboration with Dr. Prasanna Date from Oak Ridge National Laboratory. And this work is titled Adiabatic Quantum Linear Optimal Control for Discrete Time Dynamical Systems. So I know that this is not an automatic control conference, but this work is closely related with optimal control. So I'm going to be motivating the approach and talking a bit about optimal control theory. And to give you the core idea very quickly, we have tried to reformulate a classical optimal control problem, which is Toplet's least square based, in adiabatic quantum framework. And that's so that the optimal control problem as it exists today is implementable, is can be solved in the adiabatic paradigm. So I'm going to try. So what is optimal control? Well, basically, optimal control is it's a very classical, well-established domain in the automatic control area. I don't know how many of you are from automatic control, but basically, optimal control touches all the fields of engineering, be it robotics or automotive systems, and so on and so forth. And typically, the idea in uh, in optimal control framework is to design a control law or a control policy which is optimal with respect to given criteria or cost. So typically we seek designing inputs, control inputs to drive a dynamical system like a car or any dynamical system to a prescribed goal while minimizing a user-based prescribed cost. And such a cost can include system performance, energy consumption, risk, and so on and so forth. And as such, as you can see, optimal control forms is basically a cornerstone of modern control theory. And typically, the idea is to design control policies or control laws while finding the optimal trade-off between various conflicting aspects or criteria. Now, this is an AI track, so let me motivate how this directly is linked with AI. So I also work in reinforcement learning area, and reinforcement learning is nothing but learning of such control laws or control policies that are optimal. So while we are not doing learning here, but we are going to design a control law which is optimal in adiabatic modern framework. So just bear in mind that we are going to talk about optimal control theory, but in the learning paradigm that becomes reinforcement learning. So basically when you have modern knowledge, when you have data, and when you want to learn control policies, you are basically doing optimal control in the learning paradigm. But we are, in this work, we really focus upon the fundamental problem. Now, as I said, optimal control theory touches different fields of engineering, including aerospace, automotive, domain, transportation, energy grids, power sector, process engineering, chemical processes, healthcare, manufacturing systems, networks, congestion control, and infrastructure. And with the advent of uh, the industry 5.0 and IoT, we have the need of real-time optimal control with high data demand, right, or with higher bandwidth. And that calls for new computing paradigms that are hybrid in the sense that where we are able to take advantage of quantum computations, but also the hybrid, but also the classical. So that's been our motivation. And to give a little bit of context and to position the problem, in particular, we look at the finite horizon optimal control problem. So in finite horizon LQ control or linear quadratic control, we are seeking optimization over a fixed window of data. And in our case, N, the capital N, signifies the number of data. Typically, there are two broad ways to attack such a problem. One which is widely used today is Riccati-based, and that involves backward recursion of discrete time Riccati equations. Our focus is not that in this work, but our focus is on the other one, which is Toplet's least square based approach, which is slightly more archaic than the Riccati-based approach and involves solving the optimal control problem by formulating it as a least square problem. And that involves the design of so-called Toplitz system, and basically presents itself as a least square problem. But this least square problem has high complexity, has high big O, is basically, it's scales very badly with the number of data. In particular, it scales cubically with n, with the number of data, and m, the number of control inputs. So as you can see, it scales really bad. Now, we wanted to look at that from the lens of adiabatic quantum paradigm. So the idea, before going on to the main idea, let me quickly present the adiabatic quantum computing. I won't be exhaustive, and also I'm not the all quantum guy, so I'm going to be presenting at a high level. So basically, in the adiabatic quantum computing paradigm, we are solving the optimization problem by encoding them as a quantum Hamiltonian, starting from some ground state at 0 and evolving to the target Hamiltonian HP. And if the evolution itself is slow enough, then the system remains in its ground state, leading to the optimal solution. And the problem itself is formulated as a QAI, the quadratic unconstrained binary optimization, consisting of quadratic terms and decision variables or logical variables presented here as Z or C. And typically, the quantum annealers like D-wave produced by D-waves are able to typically solve such QAI-based problems. And the attractive feature here is that the time taken to solve such such an optimization is constant, is independent of the number of data the problem fits the device or is embedded. And that was our motivation. So basically, I'm not going to go much into details. The problem itself is QAI-based, so which presents itself like this, where we have quadratic terms. And let me not go much into the details, as I guess these are quite classical for you. So the main idea in this work involves formulation of the finite horizon IQ control problem, the classical approach based on block toplets least square system as a QAI, and then its implementation, its suitable modification so that it's implementable on within the adiabatic quantum framework. And that involves two basic steps. The first is the formulation as a QAI problem itself. So we do that and we formalize it, and we show that the classical optimal control problem can be formulated as a QAI problem. And then we present you the challenge as well. That leads to a challenge, in particular the control variables, they are dependent on the number of data. In order to mitigate this problem, we propose a basis function based parametrization to make this, to alleviate or remove this dependence on the number of data. So I'm going to go into details. So basically, the approach looks something like this. From the classical problem, we are reformulating it as a QAI, and then we do some modifications. I'm going to go into those details so that it's the QAI that has been formulated is suitably can be incorporated within the AQC paradigm. And finally, we come up, that leads to the control sequence, optimal control sequence with lower complexity, and we show that the time complexity is improved or is reduced. All right, so let's go into the details. The finite horizon linear quadratic problem typically presents itself in this manner. If you have done system dynamics courses, you would know that this is the first equation is nothing but the state space representation of a dynamical system, where X are the states of the system and U are these are the control inputs. So basically the states of the system, they are evolving in accordance to A, and affected by the control matrix B. Right, so we have n number of states and m number of control inputs, and we are concerned with n number of data, the big n number of data. And typically the idea is to find the optimal control law by optimizing a cost function. What is that cost function? The cost function is typically user-based, and in LQR framework, it presents itself in this manner, where we take into account the performance, the system performance, here represented by X transpose, XK transpose, QXK, and energy consumption, which is basically U square R, U transpose RU. And well, that's the typical standard way of formulating the optimal control problem as a linear quadratic regulation problem. And the objective here is to bring the system states to its zero, or the equilibrium, right? Now consider the stacked vector, control input vector, as the big U, and the stacked state vector. Using the topics approach, the most classical, the most basic approach, typically one constructs the canonical forms, the canonical matrices such as H and G, right, by stacking the control matrices and the interaction, the coupling between the two till the end of the horizon. And then we are able to express the cost function, which you see here as equation 2, as a function, as a quadratic least square form in U. This is, everything is very standard here, right? What is important is to note that this cost function is now, can be expressed as the quadratic function of U. And that can be solved using standard least square, can be solved as a standard least square problem. So in the classical framework, the computation complexity is quite high. I'm just listening to my own voice, so it's creating a little bit of echo, but I'm gonna lower my sound. So in the classical framework, we have computation complexity in this manner. It scales really bad. It's a cubic complexity in n, that is number of data, as well as n, right? And so the motivation here for us was to first of all preserve the least square formulation, so preserve the LQ structure, but encode it as a QO, and then compress the decision variables, the control inputs, in such a way that we are able to exploit the quantum advantage. And typically, if we are able to solve that in constant time, then we are exploiting the quantum advantage, right? And so in order to do that, what we do is first, we encode the controls, the control input vector, into binary variables. Okay? And so we replace the dense, nm times nm least square problem with binary optimization. This we do by approximating each control input using a fixed precision vector. This approach was proposed in Date et al. Some years back, and we leverage that approach in control paradigm. So here we use a precision vector with L real elements, right? And we use it to encode each control input using L bits or using L real elements. And we do that to each control input. These are continuous variables in distinct time. And we stack all the such control inputs in order to construct this B, right? Which, as you can see, is nothing but a stacked vector of binary variables of dimension n3. And here, as you see, by this naive transformation, we are able to express the control inputs using precision vector, using qubits, right? With a chosen resolution, choose as you want, right? We can have some finer granularity, But those are the details. The essential idea here is that we are expressing control inputs as stacked decision logical variables. But please note that here the dimension is dependent on the number of data n. So if we consider finite horizon of length n, that is with n number of data, we quickly, the number of decision variables explode to nml. So we show that by this naive transformation, we are able to transform the classical quadratic problem into a QO problem. Okay, we preserve the canonical QO structure. And this is presented as a theorem in the paper. I'm not going to go into details. We prove that by naive transformation, we are able to achieve the canonical QO form. However, the problem is that here, the number of logical variables, or binary variables, they quickly exceed the limit. We consider 64 as the limit, as the maximum number of binary variables that we can encode, that we can consider. But then I know that with some modern architectures like Advantage or Advantage 2, or with different topologies, we might be able to go till 120 or 180. I may be wrong here, but I guess 120 might be feasible. But we haven't considered that. We considered 64 based on the existing literature. And so you can see a big challenge here. Through naive transformation, we are, it's not helping us because we are dependent on n, the number of data. So in order to mitigate this problem, we propose as contribution the idea of parametrizing this, the encoding process using a basis function. So we represent the whole control sequence, not naively, but using R basis functions instead of n free variables. And we have detailed this approach in the paper, so I invite you to refer to that. But the core idea is that we consider a basis function, and we, as you can see here, alpha, which is m vector basis with m basis coefficients, which are independent of k, and then we stack them, right? And we consider the stacked time basis matrix that then helps us to express the control input. So the whole control input, the big U, is now represented by these guys, which are in turn parameterized by phi that consists of the large phi that consists of small phi's. And we parameterize each and every control input. So basically we are able to approximate the evolution of the control input in time. Now, and then we include that into the QO formulation. So we show that we can, we are able to transform the classical cost, the classical expression as a QO that includes basis functions or basis vectors. And we propose that as another theorem here, where we show that through even by incorporating the basis functions, we are able to achieve and preserve the structure, the canonical QO structure, and hence it is implementable in the AQC paradigm. So this is proved in the paper. I invite you to see. I won't go into the details here, but the key idea is there are two key ideas here. First, transforming the classical cost function as a QO, and second, using basis functions instead of the data and number of data. So we do that, and because thanks to the basis functions, we are able to decouple the number of binary variables with the number of data. So now the total number of binary variables that we have is independent of the finite horizon length or the number of data. And the number of binary variables or logical variables depend upon the number of basis functions, the dimension of the control input, and L, the precision bits. So of course, if we increase when you with a large number of basis functions, the accuracy, the approximation accuracy increases. We have seen that. For large M, it becomes problematic because you achieve the upper bound very quickly. A large number of L high resolution because the accuracy increases. We have seen that, but we haven't presented exhaustive details in the paper yet. So the next challenge the next question that comes is, okay, very good, basis functions, but which basis functions? So here we use the insight from the classical control theory, which says that optimal, the optimal control policy or the feedback control policy is basically a linear function of state itself. So this is pretty much established in the literature. In the control theory, you see that a feedback control law is nothing but mapping, a linear mapping, time varying, but linear mapping with the states. So inspired with that, we chose to use X, the states, as the basis functions. And by doing that, we not only reduce the dimensions. Instead of now playing around with nm variables, we are playing only with nm coefficient, but we also entail only, using this approach entails only quantization errors, because using state as basis functions means that we are approximating the exact control law. Now, there may be some quantization errors that will depend on the choice of the number of basis functions or the precision, the resolution. Right? So we do that, and then we do some theoretical analysis on the complexity. And here we see that while in the classical framework we have scaling, cubic scaling, or it scales with number of data, in the adiabatic quantum framework, thanks to the hardware constant annealing time, we reduce that constant to a constant value. So that's a big gain, right? So it means that we are able to scale very well, and basically the time constant is going to remain the same and independent of data. So we check that in simulation using Neil as the emulator, and so we simulated some basic stabilizable dynamical system, MIMO system, multi-input, multi-output system that generalizes the simulation study with some system matrix and control matrix. As you see, we chose some weights. Those are not crucial, but then and then we chose 3 states as the basis functions. We chose 8 precision vector elements, right? So we remain within the constraints, right, of 64, and we did some simulation for different finite horizon lengths. And so as expected, the control laws, the control inputs, they converge to 0. The states, they start from some initial states, but they converge to 0 as well. Although it is classical written, but it's really the proposed approach. But what we really, what is really interesting is to see that in the QUBO-based approach, the simulation time, the solving time, the solve time is constant across various horizon lengths. While using the classical approach, we are scaling cubically, which is, so we see this quantum advantage very, very quickly. So that's the main takeaway from this work. Of course, using basis functions entails some approximation error, But we were able to see that that the approximation error remains, first of all, constant, near constant across the horizon. We think it's because most of the approximation error comes due to the choice on the number of precision elements or the number of basis functions, and that doesn't typically depend on the number of data. And the relative error, the approximation error, the magnitude itself is not so large, well, on a relative scale, around 0.4. So that is also encouraging. We have to still investigate how we can mitigate such relative errors, or what are the reasons, what factors could amplify them. So far, we tested this on small binary variable budgets, right? But then we need to probably scale it and take other constraints into account as well. We have focused upon the finite horizon, and we haven't looked at the Riccati-based approaches, which are widely used. So currently we are looking at that. And we did all the simulation using NEAL, so probably the results may vary with different hardwares. So the key takeaways from this work are that we formulate the finite horizon least square classical problem as an exact control problem. We decoupled the binary count from the horizon length using basis functions, and for large n, the quantum advantage is clearly visible. Thank you for your attention. If you have questions, please go. Thank you.
Wonderful. Thank you very much. I think we have time for a couple of questions, if there's any in the audience here.
Yeah, thank you. So training AI models like ChatGPT and so on can be treated as a optimal control problem. Can you comment on how can you scale?
Yeah.
Can you scale your approach to train this large language models?
I'm listening to my own voice. I'm going to lower the volume. So indeed, most of the reinforcement learning problems, specifically the so-called adaptive dynamic programming based approaches that we do in our domain, they are finally solved as a regression problem or as a least square based problem. So it may be linear regression or nonlinear regression, but at the end of the day, it's a least square problem. So I believe that even there we can do something, and that's been a big motivation for me and for us, and that's why we are here. Because at the end of the day, think about fully connected neural networks. It's all it does is a linear or non-linear regression, right? So if you're able to formulate it as a least square problem, you are basically able to leverage all these novel aspects.
Okay, thank you.
Thank you for the question.
We got one more question in the room.
Hello, thank you for your talk. Super interesting. I wonder a few things, maybe two things. The first one is that the equations that you showed, the linear control equations, they resemble very, very much to some model that you obtain in open quantum systems when you're measuring, like monitoring the states. So in some approximation, which is like Gaussian and this stuff, you get the Kalman filter equations. So I wonder if you have explored this framework like as an alternative to adiabatic optimization. That's the first one. And the second one is I would like to know more about, forget about quantum and how people in the classical world solve this control problem with like what's the state of the art? Is also deep learning here or? Well, those are my questions. Thank you.
Thank you for these questions. Very interesting. Um, so I have worked with Kalman filters, and I have worked extensively with estimation theory per se, but we haven't explored it from the lens of quantum or specifically adiabatic. But thanks for the question, because it gives me some good idea. Probably there's something to look at, because finally, you are right, in Kalman filter theory, we are projecting, right? It's a projection-based approach. And what we are doing is we are minimizing the residual, right, between the measurements and the estimating, the measurement of the variable and the estimation of that variable. And we are basically reducing the residual of it. So there is something there, right? So that is some good ideas. Thank you for that. But we haven't explored. Regarding the second question. So in control theory, I do deep learning too. So we don't really. For us, learning is also can be formulated as a least square problem. Reinforcement learning is basically learning optimal control laws. So even with fully connected neural networks, these problems can be reduced to least square problems. That's where, but then again, it depends. If you're using gradient descent, it's not a least square problem. But if you're doing a batch-based optimization, it can be reduced to a least square problem. But there's a whole range of things to discuss there. Automatic control people, we don't really look at neural networks with such, with so much of critical. We just use them as tools. We don't develop. But then there's another community that really works on improving computational efficiency. So probably there we might have some.
Great. Thank you for the wonderful presentation, and thank you for all the answers to the questions. I'd like to thank the audience. This closes out the first session of this workshop.